Okay, so welcome everybody. I'm Ruth Trundley and I'm going to be doing our research talk today, which comes from a very, very specific piece of work that we did that involved a collaborative lesson research cycle, which is Japanese style lesson study that we did in this country. And it's a very specific bit of maths that we ended up looking at within this research cycle, which was part of a bigger project. And just to start us off, I'm going to get you to look at a calculation, and I just want you to work it out and think about how you're choosing to work it out, because that's going to be sort of central to what we look at in this talk. So here's the calculation. I'm going to come back to that calculation in a moment. So I said this is part of a collaborative lesson research cycle, and we had a research theme, and it was part of a project around number lines. So it's interesting that I've started with that subtraction calculation, and in fact our focus is going to be on a very specific area of subtraction. But one of the things that we were looking at within the number line project was whether understanding the structure of the number system through understanding number lines supported you to make decisions when calculating. And we'll send out these slides to you afterwards, and there's a link to our report from the number line project there. So one of the very particular things that that sort of came through this when we were thinking about subtraction was that your understanding of the number system is partly about understanding how numbers fit in with each other, how close they are to other numbers. And that positioning in the number system can be used to inform thinking and decisions when calculating. And in the case of subtraction, one of the things that most of us do as adults is we notice when numbers are close together and we decide things because of that. But what we've seen from research, and I'm going to sort of use three main pieces of research behind this today, is that children often don't take that into account when they're just looking at a subtraction that's been presented symbolically. So like the one I presented you with. So here's the first research study, Peters and others, and there's a slide at the end with all the references on. So we know that children use different strategies, and they talk about classifying those mental subtraction strategies by looking at what's the operation that's underneath it. And in that way, you get direct subtraction strategies and you get subtraction by addition strategies. So you can see there they've exemplified that direct subtraction is where you would take away parts of the second number from the first number. So for 75 subtract 43, we'll do 75 subtract 40, gives us 35. Then we'll subtract the 3 from the 35. Subtraction by addition strategies looks at going from the 43 up to the 75. So what am I adding to the 43 to get to the 75? So those are the sort of two fundamental ways that they've distinguished here in this paper. So just taking you back to this calculation we started with, which did you use? Did you use direct subtraction, taking away parts of the second number from the first number, or did you do subtraction by addition? Now I'm going to make a bold guess that you did subtraction by addition, and that's because of what you noticed about the numbers. So why do subtraction by addition? Why am I quite confident that you will have done subtraction by addition there? It's one of the things that we know is that it's particularly efficient where there's a large subtrahend compared with the difference. So their example here is 93 subtract 88. So the subtrahend here is 88, the difference is 5. So it's a small gap between the two numbers that we're looking at. And that means that subtraction by addition requires fewer or smaller calculation steps than if you were doing a direct subtraction strategy. And then in contrast, direct subtraction is more efficient when you're subtracting a small subtrahend. So 93 subtract 5. And just to go back to the numbers that we had, I'm going to suggest to you that you probably solved this in a different way than you solved the first calculation I gave you. You know, are you using direct subtraction? Are you using subtraction by addition? Have you switched for these numbers? And the suggestion from the research is that because of efficiency and what we understand about numbers and the number of steps, we will be flexibly moving between those. So again, the research shows that adults use subtraction by addition frequently and efficiently. So they're very flexible. As adults, we make decisions about how we're going to solve those. But there's quite a lot of evidence that when children talk about how they are solving subtractions, they're not using the subtraction by addition, even when the numbers are very close together. So we were really interested in this and in sort of exploring this with the children in our study, especially because we thought that if you understand where numbers are in the number system and you understand how close numbers are, that's one of the things you need to recognize in order to make the decision to solve a subtraction by addition. And then Torbens refers to this as indirect addition, which is where the sort of title of this talk came from. So this, how much have I got to add? And their studies showed that rarely, seldom, are elementary school children using indirect addition on two-digit subtractions. However, high achievers tended to solve more small difference items with the indirect addition strategy than lower achievers, which kind of gives a bit of an indication that flexibility is making calculations easier for those higher achievers, because what we've already said is the reason we choose it is it's more efficient, there are fewer steps, they're smaller calculations, it's an easier thing to do. So as part of the research cycle that we did, we used this as one of our assessment questions at the beginning. And we did a number of other things. So we knew that the children could partition small numbers. We knew that they knew sort of a number of number bonds and things, but we gave them this subtraction. And this is a year 4 class. So in that year 4 class, just under half of them were correct. So just under half got a correct solution to this. But actually analysing a bit more, it gets interesting. So nearly 3/4 used a written method for this calculation, and only about 1/3 of those children got the correct solution. So we had quite a high percentage of children choosing to do this calculation with a written method, and of those, a substantial number were not getting a correct solution. And then the majority of the others, there was a few other little ways, but the majority of the others partitioned one or both of the numbers. And in those cases, all of those children got the correct solution. So a lot of those correct solutions were coming from that partitioning of one or both numbers. But the interesting thing was none of the children chose to use indirect addition. So faced with what we think is quite an obvious calculation for looking at and saying, well, those are so close together. And the moment I think about that, I kind of see that they're only 4 apart, and therefore I've worked out the answer to that subtraction. The children in year 4 were not viewing the calculation like that at all. And I think one of the things that we wondered was whether they actually understand that they can think about a subtraction like that, that thinking about a subtraction as how close are the numbers together is one of the ways to find a solution. And McClellan talks here about if we don't teach that explicitly, it can take quite a while for children to actually realise that they can do that. And in the meantime, they're going to be doing more inefficient ways of solving those subtractions. So they're going to be carrying out subtraction operations. And then also one of the things we know is that those become embedded. They become your default strategy as well. And this is possibly one of the reasons why they said it's fairly common finding subtractions more difficult than addition, because that actually children are not recognising how they do know things that will help them find solutions much more easily to some of these subtractions. So in our research cycle, with the teachers we were working with, we worked with some maths on them first of all, and particularly looked at solving problems where you were comparing and there was a small difference between the two numbers that were being compared. And one of the things that we discovered was that when the teachers used addition to solve the problem, they were efficient, they saw it as a small difference. When they were asked to write the calculation that went with the problem, they wrote down the calculation that went with the method that they had used to solve it. So they wrote down an addition rather than recognising that the problem itself was a subtraction. So we realised, going back to McClellan, that it might be that the children are not being explicitly taught to connect this idea of indirect addition or counting up as a procedure that can yield solutions to subtractions. So this is a little bit of a transcript from, we're going to have a transcript from a problem that we did with the teachers. So this was a problem we gave them to have a think about. Each week I buy a bottle of orange juice, which costs £1.90. There's a special offer, buy 2 bottles for £3.50. How much money do you save if you buy 2 bottles today rather than 1 bottle today and 1 bottle next week? Not the problem we ended up using in the lesson, and you'll see how it was worked on and changed for when we work with the children, but we work with the teachers and we ask them to solve this. So here's a little exchange between the person running the session and one of the teachers. So it starts with the person running the session. You doubled £1.90. In my head, I said 190 and 190. So in my head, I was kind of adding it, but then I just knew it was 190, 2 lots of it, which was 380. 380. And then how did you get the 30p? What did you do then? I thought of the difference between £3.50 and £3.80. So then the person running the session says, just agree with the person sitting next to you. What's the calculation that Kate was doing? Just agree with the person sitting next to you. So the question is, when she was thinking of the difference between £3.50 and £3.80, what is that calculation that you're actually solving? Not how are you solving it, what is the calculation you're solving? And then there was a whole discussion that happened because everybody was writing additions. Everybody was writing things like £3.50 plus 30p equals £3.80. They were not writing the subtraction. And so the person in the session says, well, I'm trying to, at some point when she's really sort of trying to get them to drill down and notice this. What I'm trying to get you to notice is that when you were doing this calculation, this bit is a subtraction. Finding the difference is a subtraction. So I just wanted to sort of sit and think about the fact that in lessons we're kind of building consensus, and I've taken that notion from some of the work with some of the Japanese professors talk about what they're doing in classrooms in Japan when they're working on problems. Is this notion of building consensus, and I'm interested in where we might be building consensus in classrooms in England. And I think we may be building consensus around different things than they are in Japan. So with this problem, I think the starting point is there's a building consensus around what's the solution. And in a lot of places, that's where it actually stops. We're agreeing it's 30p. And that's it. We've got that agreement. You may have worked it out in different ways, but that's okay. We might go a step further and build consensus around the method or methods used and look at the different ways in which ones we think were efficient and which were more efficient. But it's still sort of just focused on finding the solution. What we were trying to do with the teachers here was to build consensus around the symbolic representation of the problem that has been solved. And I think this is something that maybe we don't attend to as much, but they definitely do attend to in Japanese classrooms. And this is about really connecting up the understanding of the mathematics with the symbols, so that when we solve a problem, we understand what that problem is an example of. It's an example of a subtraction. This is how we would write it. So that when we face subtractions, we understand we can think about it in the same way that we thought about this problem. So solving the problem is not the end point. The end point is actually understanding, in this case, the symbolic representation. So there'll be different things in different situations, but that was it for this one. So I just wanted to sort of like pause and think about this, about symbols, because it just linked in with a number of other things that I've been thinking about over time around reading symbols and understanding symbols and what we think it means to read symbols. So this was the calculation that we were wanting to connect to, finding the difference, comparing the prices of £3.80 and £3.50. And so there are some symbols. So reading it's about making sense of the symbols and bringing meaning, in this case, to the whole equation. And that can happen in different ways. So one way to read this is that the orange juice, which costs £3.80, is 30p more expensive than orange juice that costs £3.50. Or the usual price for the orange juice compared with the special offer price is 30p more. Different ways we can read that. So we're making sense of that back in the problem. How is this the symbolic representation of that problem? And it reminded me of Yeat Van Haar, and I put a link to the video there where he talks about the difference between spelling and reading in mathematics. And he says, if I was to look at that top one and say £3.80 subtract £3.50 equals 30p, I am spelling, because I am uttering the sound for each symbol in that number sentence. But if I'm going to read it, I'm putting sense to it, I'm putting meaning to it. And it also just reminded me this sort of struggle with understanding that when we're comparing things, the way we will record that is subtraction. There's a video I've been watching recently with Bob Moses. It's actually about algebra, and it's a fantastic video. I kind of recommend that to anybody. And again, you've got the clip there. But he talks about compared to in algebra is represented by subtraction. And that's a really key bit of understanding. And if you watch the video, you see adults again sort of struggling with making sense of the way we're talking about this situation, this context, then the mathematical language for that, and then how that is then represented with symbols. And it's not easy, that route is not easy. So again, with the teachers, we looked at a number of calculations, and we stopped and we paused at this one. And so I'm going to invite you to do the same thing. And we've thought about solving 82 subtract 77 by indirect addition. So in other words, by looking at that and saying, I can go from 77 up to 82 to solve this problem. What are all the things you need to understand and know to be able to do that efficiently? And these are the things that sort of came out of that discussion. So it starts with that thing I was talking about, which came from understanding the number system, that 82 and 77 are close together. Therefore, this is a good way to think about this calculation. Knowing that you can choose to solve a subtraction by indirect addition. You have to know that that's what you can do. I'm suggesting that for a lot of our learners, particularly in primary schools, they do not understand that. So that means we're finding how close together the numbers are. Knowing that 82 and 77 are both close to 80, and 80 lies between them. It's a key marker between them that we're going to use in solving this. Knowing it's an easy step from 77 to 80, and that's going to be based on a known fact, 7 add 3. Knowing that it's an easy step from 80 to 82, that's a bit of place value knowledge. Keeping track of the different steps undertaken. Okay, so we've added 3 and we've added 2. You need to keep track of that. And then you need to understand that knowing that the two steps together show the gap between 77 and 82. And I think you can start to see why we were looking at this this understanding alongside number lines, because a number line is a lovely model for getting that understanding of stepping from one number to another and seeing that gap. And that language of step and the gap were language we used in the number line project. And then you need to know that 5 is what you get with 3 add 2. That's a lot of different things there you need to understand and know. So there's a lot behind indirect addition, but what we found was it was that second bullet point that often is the one that children are not attending to, because when they're put in a position with a problem where the numbers are close together, but it's not written as a subtraction, they solve the problem, and they solve the problem by using indirect addition and by doing all of these. They use all of their knowledge and understanding. They just don't see it as a subtraction that they're solving. And I thought it was quite useful just to have a little look at where this sits in sort of curriculum materials, and going back to the 2015 booklets that came through from NCTM about teaching for mastery, questions, tasks and activities to support assessment. In year 4, one of the big ideas includes this. And it's that second part. Noticing the numbers are close to each other might mean this is more easily calculated by thinking about subtraction as difference. So it's, again, this is picking up on that indirect addition, but maybe I'm not noticing that 3012 and 2996 are close together. But even if I am, maybe I don't realize that I can think about that as finding that gap, looking at the difference. How much do I need to add to 2996 to get to 3012? So I'm going to take us into the research lesson and just what we found from that research lesson. So because it was a collaborative lesson research cycle, the planning team worked together over a number of sessions, looking at the mathematics behind the problem we wanted to work on, and then spent a number of sessions working on the problem and deciding on the numbers and sequencing. And the problem we ended up with is a variation on the problem I showed you earlier. So this is the problem that we decided to use for the children. Every week I buy 2 bottles of orange juice, which cost £1.30 each. This week, the supermarket has a special offer of 2 bottles for £2.39. How much money will I save this week? I think you'll see we've simplified the context there. It's the buying it every week rather than one week and one the next. That was unnecessarily complex, and the numbers here have been really very carefully thought about and decided on. So this was the problem and for the lesson, but a key part of the lesson, what we wanted to get to from solving the problem, was getting to that comparison between £2.60 and £2.39 and understanding how you write it if you are thinking about it as comparing. And we anticipated that would be the difficult part of the lesson, that the children might be fine solving the problem, but that actually how they were thinking that that problem should be represented symbolically would be the difficult bit, that they would focus, like the teachers had, on the way they had solved it rather than on what the problem was and how that could be symbolically represented. So many of the children solved the problem, but they didn't connect it to a subtraction focused on comparison. Most recorded either an addition or a subtraction taking away the savings. So here we've got £2.60, subtract the 21 pence equals £2.39. And then we've got another is subtracting the 21p, and then we've got one where they're doing the £2.39, add the 21 pence. So it was very much as we thought it would be. There was a little key bit in the lesson. I was the teacher for this lesson. So then there was a key bit in the lesson where I did the wrong thing. And I did the thing that can classically happen. And we had about 30 people observing this research lesson. And so it was quite an unusual situation, both for the teacher, both for the children and for me, sort of navigating our way with all these other people in the class. But one of the things we decided as a planning team was that we would really focus on this word compare. I'd done some work with the children before this lesson, just on language, especially things like special offer. And we'd kind of front loaded vocabulary by working on that, so that when we came into this lesson, they were already, the context of special offers and things like that wasn't going to throw them. They understood the language and the vocabulary, we hoped, wouldn't be a barrier. And we were looking for someone saying that they were comparing the prices when they were talking early on. So we had this talk going on, and in our plan, we put, for me to sort of, I've heard people say I need to compare the prices. What does this mean? What are we trying to find out? And then that I would write on the board, compare the prices. And then we would also have what calculation shows we're comparing the prices. So this idea, this notion of comparison was really key. So we needed to sort of find from somebody that they're saying comparing. Then we will make sure we understand by comparing. Let's write that up. And then we can go to, so what's a calculation that shows us we're comparing? And actually we'll write equals 21p. So what's the calculation that shows us the answer 21p, that we're going to save 21 pence? That was our plan. And you will see that that's sort of what happened on part of the board. But we had a little bit of an issue around the language, and what I didn't do was what I would normally do, and that is go with what the children came up with. So I listened for compare. Nobody used the word compare, but they did say difference. And at that point, what I should have done was followed the children and used the word difference rather than sticking with our compare word, because it meant the focus on the meaning got slightly undermined. The language that had emerged from the children, that kind of showed their understanding and that they were familiar with, at that point, at the tricky point of understanding and trying to link to the symbols, I didn't pick up on and use. I went back to what we had planned for. And so this idea of comparing the prices, the compare word was one that we hadn't really invested in enough time in understanding. And that therefore was sort of slightly in the way of the understanding of what we're trying to get to with writing the problem. But some of the children did write about difference in their writing about the problem. And we asked them to write at the end what they had noticed when we'd worked on this together, and we'd looked at people's explanations, and we'd considered what was going on in the problem, and we came to writing this subtraction and looking at how that fitted on the number line. Where was that 21p on the number line? What was that about? We did get children writing about difference at the end in what they had noticed. So I've noticed there's a difference of 21p from £2.60 and the special offer of £2.39. You're saving 21p because the difference between £2.60 and £2.39 is 21p. And there's some other children sort of noticing different things, and they've got some interesting terminology. We've got 2 children here talking about rounding to the closest 10, and actually what they mean is they mean adding to that 10, go into that 10, the 1p up to the £2.40. That kind of helps you to get there. Their language was rounding, but that's what they were doing. They were doing that adding step. And then we've got somebody here who's drawn a number line and saying, I've noticed that 21p is between £2.39 and £2.60. So understanding where that 21p fits, and that is the difference, the gap between the 2 numbers. It was quite interesting, you can, if you go to the report, you can read more about the lesson research cycle and the research lesson itself. This was really interesting. There was a child that somebody observing had said they didn't seem to really be involved, and they didn't really talk to their partner at the partner talking times, but this is what she wrote at the end. And she had this she managed to articulate a very clear understanding. She used that subtraction as her starting point, and then explained how she knew that adding to the £2.39 got you to £2.60. So we've got that connection there between the method and the problem that's being solved. So just to finish off, I just wanted to say sort of where my thinking is with this, and thinking about this whole what's the actual problem we're solving and how you're solving it, and trying to connect that. And this sort of issue around the symbolic representation of problems. I've gone back to a model that we've used for many years now, that we adapted from Haylock and Coburn, and we adapted it over time using it. But they in their work talked about when children develop an understanding of concepts, they need to understand different aspects and join that all together. We refer to this as the connective model, because what you have is you have different elements and they're all connected with each other. And I like to think about it these days as it's sort of CPA plus, because you've also got language in there. But one of the things I think this model makes very clear that people miss about CPA is it's not one directional. Everything is connected with everything else, and you can move in different directions. Looking at what we did with this lesson research cycle and what was emerging from it, and the research we looked at beforehand, and going back to this model, I think this is what's actually going on, is that the children are solving the problems, they're understanding the context, they can connect that with the number line, they can connect that with different images, structured images, they can explain their thinking, they can work out the solution. But there is a disconnect between that and the symbolic representation. And what that means is, if those experiences are not being connected to the symbols, when you start from the symbols, they haven't got those experiences to draw on. They've got a very limited view of what those symbols are representing. So it feels to me that it's all about those dotted lines. And I've just posed this question because it's kind of a question I've been posing myself, really, is how much do we focus on building consensus around the symbolic representation of a problem rather than the solution, in order to understand how to read the symbols. So in other words, rather than this is how I did it, what is the problem I've just solved? How would that look if it was written down as symbolically as a question for me to answer? And that's sort of where that's taken my thinking. So as I said, we've put the 3 main papers that have been referenced in there here on the last slide. And that's the end. So what I'm going to do, I'm going to